Welcome to the class. Dear students, today's class we will discuss coordinate covalent compounds. In coordinate covalent compounds, we are first going to see the introduction of coordinate covalent compounds or coordinate covalent bonds. We will see some examples of coordinate covalent compounds, and then we will get introduced to some terms such as the coordination sphere, the coordination number, different types of ligands, and coordination polyhedron. All these terms we will look into, and finally we are going to see the properties of coordinate covalent compounds. So let us start coordinate covalent bond. So how it is formed? It results from the donation of a pair of electron from one atom to another. What happens here? A pair of electron is donated from one atom to another. Of course, the another atom, which is which is of concern here, it accepts that pair of electron. So one atom donates, the other one accepts. One atom donates a pair of electron, not one electron. It donates a pair of electron to another atom. So that is how coordinate covalent bonds are formed. So there are two kinds of atoms here. One is the donor atom, the other is the acceptor atom. In this process of donation of a pair of electron and acceptance of a pair of electron, both the donor atom and the acceptor atom achieve stable electronic configuration in the outermost shell, or they achieve inert configuration, a configuration of inert gas. Okay, the molecule becomes stable. Okay, and how is it represented? It is represented by arrow. It is represented by arrow like this. The head of the arrow will be directed towards acceptor atom. The tail of the arrow is directed towards the donor atom. Okay, the head of the arrow is directed towards that atom which accepts the pair of electron. So that is how it is represented. So this is the introduction of coordinate covalent bond. What have we discussed? We have discussed that it is resulting from donation of pair of electron. Okay, not one electron, a pair of electron is donated, and a pair of electron is of course accepted on the other side. The donor atom is the one that donates, the acceptor atom is the one that accepts. Both of these, by doing this, they achieve electronic configuration that is stable. That is, either they achieve their octet or their duplet. Okay, that is, they achieve their configuration of inert gas. And how is it represented? By arrow. Where is the head of the arrow oriented towards? It is oriented towards the acceptor atom. Let us better understand coordinate covalent bonds by looking at certain examples. The first example we are going to discuss here is ozone. Okay, ozone. You know the formula of ozone? Yes, O3. Okay. And what is the atomic number of oxygen? 8. Can you draw its electronic configuration? 1s2, 2s2, 2p4. Right? So what will come like, if we draw, it would come like this, right? Okay, this will be divided. So what is the valency of oxygen? How many valence electrons are there? Yes, there are 2 valence electrons. Okay, so we need at least 2 more electrons so that oxygen achieves octet number. Right now in the second shell there are 6 electrons. So to achieve this octet number in outermost orbit, we need 2 electrons. So someone needs to fill in this space. The only way for the oxygen to do is to share these electrons with the electrons of other oxygen atom. To share these electrons of these orbits. Which are these orbits? Py and Pz orbits. To share the unpaired pair of electron of Py and Pz orbitals with unshared pair of electrons of Py and Pz orbitals of another oxygen atom. Right? So another oxygen atom I am going to draw. Now let them share these. Right? Let them share this. This is of opposite spin. Let them share this. So now these 2 oxygen atoms they can go for mutual sharing of electron, right? This can share its electron with this can share its electron with, they can go for mutual sharing of electron. In this way they would become oxygen molecule, and in this way this oxygen reaches its octet configuration in outermost shell. So similarly this oxygen also reaches octet in its outermost shell. Both of these oxygen reach octet configuration in outermost shell, so they are stable as a molecule. Right now this molecule's outermost shell is like an inert gas outermost shell, correct? It is equal to inert gas configuration. So oxygen as a molecule is of course stable, right? So this is what has happened, right? Double bond, right? One is sigma bond, the other is pi bond, fine. And each oxygen has got two lone pair of electron, right? This is the first lone pair of electron, this is the second lone pair of electron, and these are these electrons which have gone for mutual sharing and they have formed bonds. Two types of covalent bonds are seen, one is a sigma, the other is the pi bond. Now both of these oxygen have achieved its octet configuration. Now in presence of UV light, suppose this reaction is occurring in stratosphere, okay, in the presence or in a lab under UV light. In UV light, another oxygen molecule with two lone pair of electrons, it would also attach with O2 to become O3. But to attach with O2, what it have to do, that is it has to achieve inert configuration. Only then it will attach here, right? This oxygen also needs to complete its octet configuration, and for achieving that octet configuration it has to do one thing. That one thing is that it has to accept a lone pair of electron from either this oxygen atom or this oxygen atom. So suppose it is accepting from this oxygen atom. Let us see this scenario. Yes, now it has achieved, yes, see, one lone pair of electron, it has been donated to this oxygen atom. So when its lone pair is intact, so when this lone pair of electron is donated to this oxygen atom, of course this oxygen will become positive because it has given its lone pair of electron. And this oxygen, it has achieved stable octet configuration because it has taken two electrons. It needed two electrons, right? This also needed two electrons, it got it from this. This also needed two electrons, it got it from this. Their octets are complete, they have octet configuration, and there is no disturbance in that, provided that there is a lone pair of electron with each oxygen, and one of the oxygen donates that lone pair of electron to the third oxygen atom. With the result, the third oxygen atom's octet, its requirements are fulfilled and it achieves octet configuration. This oxygen doesn't have any, it doesn't affect its octet, its donation doesn't affect its octet configuration, but it achieves a positive charge because a lone pair of electron has been given. So now we get O3 molecule, which is a coordinate covalent compound, which is a coordinate covalent compound. I hope you got it. That what I said is oxygen's atomic number 8. Valence is 2. The valence electrons are 2. It needs to get 2 more electrons to complete its octet. So it will go for mutual sharing of electron with another oxygen atom. Okay, with the corresponding orbitals. It will form O2. O2 is stable molecule. It has got inert configuration, inert gas configuration, because both the oxygen atoms have achieved their octet configuration. But in the presence of UV light, or if it is carried out in stratosphere, if this process is occurring in the stratosphere layer, then what would happen? This oxygen atom would go for combination with oxygen molecule, but it would only do so if its octet configuration is fulfilled, right? If its demands are fulfilled. So what it will do, it will accept a lone pair of electron from either of the two oxygens, right? The oxygen which donates that lone pair become positive. There will be no effect in its octet configuration. So that is how the molecule of O3 is formed. This is a coordinate covalent compound. right? I hope you got it. There are other examples of coordinate covalent compound. I will tell you the second example. Look at this nitrogen. Its atomic number is 7. So that means there are 3 valence electrons. I'm going to draw the 3 valence electron. And there is a lone pair of electron in the 2s2 orbital. I'm going to draw it like this. Fine. So there are 3 valence electrons. It needs 3 more electrons to make its octet configuration, to achieve octet configuration. So it can go for mutual sharing of electron with hydrogen atom. Okay. So if it goes for mutual sharing of electron with hydrogen atom, its octet is complete. It achieves octet configuration in outermost shell. It as a molecule is stable. NH3 is stable. It is having octet configuration in its outermost shell. Now, if this is exposed to acidic conditions, then what would happen? That is a question. In that case, you can see that the H plus is unstable. Okay, it needs to complete its duplet configuration, 2 electron in the outermost shell. The only way to do is to accept the electron pair from here. So what would happen? Yes, it would accept the electron pair. These are all covalent bonds and this is the coordinate covalent bond, right? The nitrogen acts as donor atom. It donates the pair of electron to hydrogen, and because it has donated its lone pair of electron to hydrogen, the nitrogen becomes positive. Nitrogen becomes positive. Hydrogen's requirement, is it fulfilled? Yes, it has achieved the configuration of helium. Has nitrogen's requirements been fulfilled? It has already been fulfilled here, right? So now we can see another coordinate covalent compound, NH4 plus. NH4 plus. Similarly, you can see in nitric acid. So this is nitrous acid, right? And these are the lone pair of electron in nitrogen. Okay, there were 3 valence electron, okay, of nitrogen. So now as a molecule, nitrous acid is okay. It is stable. It has got inert configuration in outermost shell. What would happen if there is one more oxygen atom? Oxygen wants to complete its octet configuration. The only way to do is to accept it from nitrogen, right? So what can happen now? Yes, right? So now you got HNO3, right? So you can see another coordinate covalent compound here. Okay, so these are the examples of coordinate covalent compound. Similarly, you can see this reaction between NH3 and BF3. This is BF. Okay, now what can happen? Yes, this can donate, nitrogen can donate, and what we get here? Now we get something like this, right? So these are all coordinate covalent compounds. All of these are coordinate covalent compounds. Dear students, now you can see what is happening here. The nitrogen is getting positive. I forgot to put it. And here also nitrogen gets positive sign because it has donated its lone pair of electron. So there are two things that I want to say here. Just look at this reaction. Forget about this. Look at this reaction. Two things I wanted to say. Can you see which kind of substance is this? This is a substance that donates a pair of electron. Okay, what do we call a substance that can donate a pair of electron? What do we call a substance that can donate a pair of electron? Are you able to remember it? Yes, we call it Lewis base. We call it Lewis base. And what do we call a substance that can accept a pair of electron? We can call it a Lewis acid. And what is the result? The result is coordinate covalent compound or coordination compounds. Okay, so you can say that coordinate covalent compounds or coordination compounds result from reaction between a Lewis base and a Lewis acid. It results from reaction between Lewis base and a Lewis acid. Am I right? See, this is the Lewis base. It can donate a pair of electron, and this is the Lewis acid which can accept a pair of electron. This is the Lewis base which can donate a pair of electron. This is the Lewis acid which can accept a pair of electron. One more example, a very interesting one that I want to show you. This one. This is our water, right? Now we are going for a coordinate covalent compound H3O plus. Correct? This is H3O plus. See, it has water molecule is stable. It was already stable, and H plus we are introducing from outside. We are trying to protonate water. We are introducing acidic condition. H plus, what it would do? It would go and take the lone pair of oxygen. In that way only H can become stable. It can attain duplet configuration. Of course, it won't affect the octet configuration of oxygen. Okay, so there is no problem for oxygen if it donates a pair of electron. Okay, but this oxygen would become positive in charge. So this is also an example of coordinate covalent compound. Here also what we are seeing is that this acts as Lewis base because it donates a pair of electron, and this acts as Lewis acid, and this is the coordinate covalent compound. So the coordinate covalent compound is a result of reaction between a Lewis base and a Lewis acid. Another thing that I want to tell you is that the whole of this molecule is not donor atom. Is it donor atom? Is the whole molecule donor atom? No. It is in this molecule that only nitrogen acts as donor atom. Okay, the molecule as a whole is called as the ligand molecule, and the donor atom here is the nitrogen atom, and most of the time the acceptor in coordinate covalent compound is called as the metal ion or the central metal ion. So central metal ion are those elements which are called as transition elements in the periodic table. So this includes calcium, magnesium, aluminum, zinc, nickel, cobalt, okay, etc. So these are the transition elements. They act as central metal ion. And ligand is the molecule that has the donor atom in it. So ligand is actually acting as a donor of a pair of electron. Now for the ligand to act as donor, it should have what? It should have a pair of electron. So ligands are of two types. One is simple anions. Okay, they have a pair of electron. They are negatively charged. Examples are Cl minus, correct? F minus, I minus, acetate, CH2CO minus. So they are simple anions. They have electron pair, and they can very well donate their electron pair. They are simple anions. The second type of ligand is the neutral molecules which have lone pair of electron. Neutral molecules that have got lone pair of electron. Examples of this is NH3. See, it has got a lone pair of electron. H2O. Correct? So ligands are those which can donate a pair of electron. For donating a pair of electron, either it can be a simple anion which has got a pair of electron, or it can be a neutral molecule which has got a lone pair of electron. So these are the two types of ligands that we encounter. Now ligands can be further classified depending on how many sigma bond it is able to make with the central metal ion. Okay, so how many sigma bond it is able, or how many linkages can it make with the central metal ion. So this is the central metal ion, this is the ligand. Okay, if it is able to make only one linkage, then it is called as unidentate ligand or monodentate ligand. Okay, example of this is Cl minus. It can only make one linkage with the metal ion. Or I minus. What about F minus, Br minus, iodine minus? Oh yes, it is already written. CH2CO minus. Okay. Okay, what about NH3? Only one it can make with metal ion. What about H2O? Right? So these can only make one you can say one linkage with the metal ion, or that is why it is called as unidentate ligand. Unidentate ligand. Now others are called as polydentate ligands. That is more than one linkage it can form, or that is it can form more than one sigma bond with the central metal ion. Okay, more than one sigma bond with the central metal ion. Okay, in polydentate also it is further classified as bidentate. That means it can go for two linkages. Okay, let's see an example. OCO minus oxalate. Okay, this is the oxalate ion. And let us look at another example. This is NH2 CH2CO minus. Okay, glycinate. This is a neutral molecule that can donate a pair of electron to metal ion, and this is a yes, it is already having a simple anion type of structure. So both can go for this thing, donation of electron. So this is a bidentate ligand. Let us now go for tridentate ligand. Two linkages in bidentate. Let's look at tridentate ligand. It can form three linkages with metal ion, or it can form three sigma bonds with the metal ion. Let us look at the example of tridentate ligand. That is diethylene triamine. Let us look at this structure. Let us look at this. Look at this structure. 1, 2, 3. Diethylene triamine. How to say it? Diethylene triamine. So if there is a metal ion here, yes, it can contribute from 3 spots or 3 coordination positions. Okay, the position from which the electron pair is being donated, that is called as the coordination position. Okay, so it can donate electron from 3 coordination positions. So it is a tridentate ligand. Therefore, it forms 3 sigma bonds. Right, so it is classified depending upon how many sigma bonds is being formed with the metal ion, right? Or it is classified according to the linkages that is formed with the metal ion, right? Now there is tetradentate ligand also. Tetradentate ligand also, it can form 4 linkages with the metal ion. 4 linkages. Let us look at an example of tetradentate ligand. Tetradentate ligand, that would be triethylene tetraamine. Let us look at this. Triethylene so this is an example. Okay, this one side, two side, third side and fourth side. Tetradentate ligand. So 4 linkages can be formed with the ligand. 4 sigma bonds can be formed with the ligand. So this is 1, 2, 3 triethylene, 1, 2, 3, 4 tetraamine. Triethylene tetraamine. Now we have got a hexadentate ligand which is very famous. Hexadentate ligand which is very famous. Hexadentate. A very popular one which is used in complementometric titrations. So that is diethylene amine tetraacetate or EDTA. Look at this. This is the structure. Yes. See, EDTA, diethylene amine tetraacetate, right? Diethylene amine tetraacetate, EDTA. It can donate 6 pairs of electron and it can form 6 linkages with the metal ion. What are the 6 spots? Spot number 1, coordination position 2, coordination position 3, coordination position 4, coordination position 5 here, coordination position 6. So there are 6 coordination positions with the central metal ion, right? So in this way it is classified. So this is of particular interest in complexometric analysis of metal ions. Okay, so like calcium, magnesium, we can use to quantitatively detect. Okay, it is used as titrant to quantitatively detect the traces of metal ions present in the solutions, right? Now, polydentate ligand, when it forms linkages with metals, right, what we have seen is that it leads to formation of rings, stable rings actually. It leads to formation of rings, and such rings are called as chelates. Such rings are called as chelates, and the process of incorporating a metal ion into these rings or into chelates is called as chelation. And the agents such as these, which is used to chelate a metal ion, are called as chelating agents. So what I am going to repeat, what we have seen here is that in case of monodentate, rings are not formed. But when we are talking about polydentate ligands like bidentate, tridentate, tetradentate and even hexadentate ligand, what we are seeing is that it is forming more than one linkages, and that leads to formation of rings. That rings are stable and these rings are called as chelates, and the process of incorporating such metal ions into stable rings or chelates is called as chelation. And because these used for formation of chelates, they are called as chelating agents. So that is what is chelating agents. Now there are some terms in these. The first term is coordination number. What is the coordination number? Coordination number. So coordination number is nothing but the number of sigma bonds that metal ion makes with ligand. That's the coordination number, right? If it is making 2, then it is a coordination number is 2, right? If with a single ligand it is making 2, then coordination number is 2. So what I have said is number of sigma bonds that metal ion make with ligand, right? So the total number of sigma bonds that the metal ion makes with the ligand or forms with the ligand is called as, sorry, the arrow is like this, is called as the coordination number, or number of ligands that surround the metal ion is called as the coordination number. There is another term called as the coordination sphere. Okay, so this is the metal ion, this is the ligand. Okay, so when they are written in brackets, right, suppose like this, and charge, when it is written like this, then the total this thing and the in bracket is called as the coordination sphere. That is, coordination sphere is used to represent metal ion and its ligand, to how many number of ligand it been attached to, and the charge of the complex in brackets. So that is what is coordination sphere. Now coordinate covalent compounds, after their formation, these coordinate covalent compounds are actually directional in shape. Okay, so therefore after the formation of coordinate covalent compounds, we get some geometrical shapes. These geometrical shapes are called as coordination polyhedron. Coordination polyhedron. Okay, So after the formation of coordinate covalent compounds, we get some definite geometrical shapes of coordinate covalent compounds, and these definite shapes are called as coordination polyhedron. So we have got this square polyhedron. So square polyhedron would look like this. Okay, this is the square polyhedron structure of a coordinate covalent compound. This is square polyhedron. We have got tetrahedron structure. It would look like this. This is the tetrahedral structure. Okay, tetrahedral polyhedron structure. Okay, and we have got square pyramidal structure also. In square pyramidal structure, what would happen? One ligand would. This is the square pyramidal structure, right? This is the square polyhedron, and this is square pyramidal polyhedron. This is tetrahedral polyhedron. So what we are seeing is that after the formation of coordinate covalent compound, they go for definite geometrical shapes, and these definite geometrical shapes are called as coordination polyhedron. Dear students, these are the terms that are associated with coordinate covalent compounds. Now let us go for the properties of coordinate covalent compounds. Properties of coordinate covalent compounds. Now coordinate covalent compound has got same energy as that of covalent bond, because they are nothing but covalent bond only. So they have got same energy as that of a covalent bond. There are two things that are different. Number one is that coordinate covalent compounds are colored. They are colored. Okay, that is when visible light is passing, when there is a visible light that passes through the central metal ion in complex, when it is in complex form. Otherwise it won't be. Okay, if it is individual metal ion, it won't show any color. But when the metal ion is present in a complex form, what happens is, when we are passing the visible light, what happens is, actually in metal ion there are electrons in d orbitals. Okay, lower d orbitals are having some electrons. Okay, lower d orbital 1, 2, 3, 4, 5. So lower d, there is unpaired electron in the lower d orbital. So when visible light passes, it absorbs certain lambda, radiations at certain lambda. Okay, and this jumps to higher orbitals. Okay, so this amount of energy is actually fixed. The energy needed to jump from lower orbital to a higher orbital is actually fixed. Correct? So this energy is otherwise quantized, right? So therefore the lambda also will be fixed. The lambda, that means the absorption at a particular lambda therefore will be fixed. So only that rays at a particular lambda would be absorbed, and others won't be absorbed. Correct? So we will get a color that will be complementary to the lambda that has been absorbed. Right? Only one. See, visible light is made up of 7 colors, right? So if only one of wavelength is absorbed, there will be deviation in the color of the visible light. So that is how these coordinate covalent compounds, they show color. Okay. The second thing that makes it very different is that they are magnetic in structure. They are magnetic in nature. Why they are magnetic in nature? I already told, there are unpaired electrons, right? So this would attract, okay, it to opposite charges. Correct? So that is why these complexes are magnetic in nature. Dear students, I hope you have understood and I hope you have liked the class. If you have done so, please do not forget to subscribe the channel. Please do like and share the video. Thank you very much.